Alrighty, here I am with the 2022 TGC derived grade bonding exam. So we're going to start at question 1. So what we needed to do in this table here was make sure we understood about metal and non-metal. So calcium is a metal, iodine non-metal, that makes this one ionic. This one, calcium is just a metal, so that's metallic. And then we've got iodine, so I is just a non-metal, so that is molecular. So once we've worked that out, we just need to be really, really consistent, and we have to get this table right. If we get this table wrong, the rest of this question is going to be wrong. So it's really, really important. So ionic, the particles are ions, and the attractive force are ionic bonds. Pretty straightforward. Metallic, we've got metal atom, and we've got a metallic bond, and then molecular, and then we've got molecules, and we've got weak intermolecular force. Don't abbreviate this, I'm just abbreviating it for this video so it goes a bit quicker. All right, really, really important to get that right. The rest of this question is essentially taking this information in the table and just expanding on it and making the clear links between this, which is the structure and bonding, to the properties. So in this one here, we're looking at our ionic and we're looking at our molecular substance. If you didn't know what sublime meant, you just needed to read changes from a solid to a gas. So we're looking at something that's going from a solid, remember that's fixed lattice form, to a gas where no particles are attached. And a melting point is, of course, the fixed lattice going to a not quite so regular structure. We've still got bonding in between the particles. Okay, so take the table, put it into sentences. So calcium iodide is an ionic substance or solid, and we're going to continue the sentence, composed of a 3D lattice, that's its regular structure, of ions bonded together by strong ionic bonds. Okay, so there is our structure and bonding, and it's come directly from the table. So get the table right, put the table into words. Now we need to take this. Sometimes we need to add a little bit more in here, not really so for the ionic, but we're looking at its melting point. So we need to say ionic bonds are strong. And we need to say, therefore, a lot of heat energy is required to break or loosen some of the bonds and change calcium iodide from, sorry, my cat was just trying to bust its way in then, calcium iodide from solid to liquid. Right, and then we need to do a very similar paragraph for iodine. Just be aware when you're talking about iodine molecules, you want to make sure that you are clear that the width are between the molecules. Okay, so that's really important. And we're talking about not breaking or loosening. We're talking about breaking all those bonds, as remember we're going straight from a solid to a gas where there's no forces between the particles. Right, so over here we're still relying on the table on the second page, but this time we've got the metal and the ionic. So we've already talked about the ionic substance over here, so let's talk about the metallic. So the metallic substance, so we've got calcium is metallic. So it's a 3D lattice of metal atoms or calcium atoms bonded together by strong Some of you wanted to say non-directional, and that's fine. Let's put that in, non-directional metallic bonds. We do need a bit extra here. The metallic structure, there are delocalized valence electrons. So that's a key point in this question here. Okay, the non-directional is not really relevant to electrical conductivity. So you can put that in, but it isn't actually going to help your electrical conductivity. That is to do with malleable and ductile. So we're going to leave that one there. So we want to talk about conductivity requires moving charged particles. And we want to clearly identify these moving charged particles as the delocalized valence electrons. Now these are delocalized, so they are moving, whether calcium is is a solid form or liquid form. So that is why calcium can conduct when solid or melted or molten liquid form. However, in calcium iodide, we've got to be really clear. I'm not going to repeat the structure here. We just did that back over in the first one. So calcium iodide, we need to be really clear that the ions are the charged particle and that in the solid, these are locked into the lattice and can't move. Okay, so when we melt an ionic solid, that allows those ions to move. That's the key idea there. Right, so that's pretty much that. Let's go on to the next question. Don't forget, you should have access to the marking schedule for a little bit more detail. These are just hints. Right, so Lewis diagrams. These are really important to know, but mostly you don't have to carry on with them. So let's just go through them. O3 is quite a hard one. So we know that oxygen has 6 valence electrons, each of them. So the ones on the outside are going to need an extra 2 to make their 8. And we always draw electrons in pairs. So 1, 2, 3, 4, 5, 6 from that oxygen and 2 from that oxygen. So now this one's got 8. If I did the same over here, I would make this atom have 8. But then I'd have too many around the centre. So I'm going quite quickly here. So we needed to shift these 2 electrons from this atom out to here, keep them in pairs. So look, all of those oxygen's electrons are around just that oxygen. And this one here has got an extra 2 electrons, which it's donating in here, and then 2 of its own. Right, so that one's a tricky one. That's your coordinate or your dative bond. This shape is bent. Your CO2, I'm going to draw this one with 2 lines for a double bond. Your CO2 should look like that. I think everyone was pretty good at doing that one, and that's linear. And your NCl3, 3 single bonds. Don't forget to draw the non-bonding electrons. Lots of you forgot to do those. Okay, so those halogens, and then also that nitrogen has 2 electrons around it, and that is a trigonal pyramid. In the next question, which is your bonding and shape question, we really needed to make sure that we linked the correct ideas. So there's 2 ideas. So the first one is the total areas of electron density, which are around the central atom. So make sure you get all of that in, obviously not abbreviating it. So these total areas repel, or we like to say occupy positions to minimize repulsion. That's the best way to say it, I think, to minimize repulsion. And at this point, we should link this to the parent shape and the bond angle. So for instance, if we're talking about OF2 up here has got 1, 2, 3, 4 total areas of electron density around the central atom. So let's just say that we're talking about OF2. So that's going to be a tetrahedral arrangement. And it's going to have bond angles of 109.5. Is that cat doing? Angles of 109.5. Excuse me for a second. What are you doing? Please. There we go. Right, sorry, I'm back. Okay, 109.5. And the second idea is that we then look at the number that are bonded and non-bonding to give the molecular shape. Okay, so 2 areas are bonded and 2 areas are non-bonded. And that gives us our molecular shape. So therefore, our molecular shape is bent, which we know because the question told us that. So a couple of little things there. Please don't just restate the information in the table as your first sentence. So don't write OF2 has a bond angle of 109.5 and is bent. We know that. We can read the table. So it's really important that you explain why. So I've just done the 2 separate ideas for OF2. You would also need to do that for COF2. So 3 total areas of electron density around that central atom, occupying positions to minimize repulsion in a triangular planar arrangement with bond angles of 120. And then the second idea, because all 3 areas are bonded, the molecular shape is also trigonal planar or triangular planar. This does ask you to talk about explaining the difference. So I would have liked a sentence at the bottom just summarizing the main differences. Over here, this is our polarity question, and actually it was a nice simple polarity question. This one here is non-polar, this one is polar. And again, we've got 2 ideas. So the first idea is the idea of are there polar bonds? And we should know that there are always polar bonds if the 2 atoms that are bonded are different. So let's do water. So there are 2 polar bonds, and that is because the different electronegativity of H and O. You might know that O is more electronegative than H, and you can write that in, but it's okay just to say the different. Right, so the second idea is, actually just go back to the first one. This creates a dipole, which is a separation of charge. Okay, so the second idea is, does the shape mean these dipoles are arranged symmetrically or asymmetrically? Arranged symmetrically or asymmetrically. Okay, so you do have to actually mention the shape. So that's really important. So in water again, we would say as the shape is bent, this means that the dipoles are arranged asymmetrically, they do not cancel, and therefore H2O is polar. So that's the steps we go through there. So I just did a generalized statement there. You can look at the actual marking schedule to get the actual answer. Okay, so it's a pretty fair exam so far. Then we get to our first calculation. So it is really important in our calculations that we know what all of the numbers stand for. So we've got 14.7 grams here, which is a mass, a little m. We've got a molar mass, which is a big M. Soon as I see a little m and a big M for the same substance, I can do N equals little m over big M. Okay, so when I get N equals little m over big M, I'm going to get 14.7 grams over 40.1 grams per mole, and that's going to give me 0.367 moles. All right, so that's my first idea. A lot of you got that. I then need to look at what the equation tells me. This question is about calcium, so I need to find calcium in the equation. 1 mole of calcium will release 700 kilojoules. I'm going to write that down. 1 mole of calcium, this is from the equation. 1 mole of calcium releases 700 kilojoules of energy. We've only got 0.367 moles of calcium. So if we have a little look of that, we know that that's about a third of that. We've got 1 there, we've got about a third. So that's going to be about a third of that. Okay, so just if we know that in our head, we can check whether our answer's right or not. So I just do a relationship. How do I go from there to there? I multiply by 0.367. So I'm going to multiply by 0.367 there. So 700 times 0.367 kilojoules is going to give me 257 kilojoules. So does that look about right? Is that about a third of that? Yep, that's pretty good. And I'm going to say that's released. I'm not going to give a delta H and a negative here because it asks for the heat energy released. It does not ask for an enthalpy change. If it asked for that, then I would have to give delta H equals positive or negative something kilojoules per mole. But this did not ask for that. Okay, last question, question 3. This one should have been quite straightforward, exo or endo. We've got a delta H negative, so I'm going to go exo as delta H is negative. Literally, that's all we need there. And I know because it's exothermic, the shape of my graph is going to be releasing energy. I have to show reactants, products, and delta H. Reactants, products, obviously turns from reactants to products. And the difference between the two is our delta H. Want to get more specific? I can put that number in, negative 177. And if I want to be more specific, there are my reactants. I could draw those in there. There are my products. Oh, sorry. I could draw those and put them down there. Okay. All right, down here. This is a solubility one, so that's quite tricky. So what we need to do here is look at the question we've got, and actually quite a few people wanted to call this ionic. Non-metal, so molecular. Okay, non-metal, molecular. And the other substance we've got is water, which is also molecular. So what we're looking at here is whether these things are polar or non-polar. So we have to make a pretty quick decision here. But what's going to help us, I mean, we should know that water is polar. And we should know that polar things dissolve in polar molecules. So if ammonia is soluble in water, we would expect ammonia to be polar. If we really wanted to check that, we could draw a little Lewis diagram and we could have a think about that. But it is polar. CO2 is not readily soluble. That is indicating that it's non-polar. Don't forget we've also drawn CO2 back in a previous question, so you can go back and check that. Okay, so we don't want to say why these are polar or non-polar. That's in a previous question. All we want to talk about here is why things dissolve or don't dissolve. So let's take the CO2. So there's some CO2 molecules, and there's CO2, they're bonded to each other. And they're bonded by some kind of whiff. All right, we're trying to add it to water. There's lots of water molecules, and they are bonded to each other by some kind of whiff. This does not happen. Okay, if it did happen, what we would be expecting to see is that the CO2 and H2O are all bonding to each other. So the key idea in this question is that the forces between the CO2 molecules or the forces between the water molecules must be stronger or more favourable than the forces between the CO2 and H2O. It is not correct that there are no attractions between the CO2 and H2O. There are attractions. They are just not as good as either these ones or both of them. Right, in this case, I think it's these ones that are the better ones. So that's our key idea there, and I've just gone through it really quickly to give you the main ideas. That's the kind of diagram you would want. This is a trickier one than the ionic. So go back to the marking schedule again to look for the exact wording of that question. Okay, and you did have a lot of space for that. So that actually shows you that you did need to write a fair bit. Okay, a couple more calculations. This one's very similar to the first calculation that we did, but it's backwards. So we needed to, this one here, we haven't got anything. We've got a big M. that's some kilojoules. So we can't actually start with N equals M over M here. So we've actually got to start with our equation. Right, so from the equation, okay, and we've got to find out what is it that we're looking at. We're looking at NH3. So we've got 4 moles of NH3 from the equation, releases 912. Okay, so if I get a number that's not a 1, probably the easiest thing I do is to turn that into a 1. So therefore 1 mole of NH3, so I've divided that by 4. I'm going to divide that by 4. And I'm just going to grab my calculator to work that out. Is 228. So that tells me 4 moles releases 912. That came out of here. Therefore, 1 mole releases 228. So that's about a quarter, right? So that's about right. Good. That's released still. Okay, back to the question. We want to know how much NH3 produces 658. So how many moles produces 658 kilojoules? Right, so let's work out what this has to be. So what do I times 228 by to make 658? It's going to be about 3. So if I just go over here and I go 658 divided by 228, is that 228? Yep, that gives me 2.89. That's about 3. So if I times that by 2.89, that gives me that. So I'm going to times this one by 2.89. So it must mean that 2.89 moles of NH3 must give me 658. That's not what the question wants, but now I've got moles, which is N. I've got molar mass, which is big M. So little m equals N times big M. 2.89 moles times 17, which equals 49.1 grams to 3 significant figures. It was a tricky one, but I know you can do that one. Okay, and then, is this the last question? Yep, so this is our bond enthalpy question. And this was a tricky one because they gave you the answer and you had to work out one of the bonds in here. But I was really proud of how many of you actually pretty much got the way you did it right. So I'm going to set it out very carefully. I'm going to put the bonds broken on this side because that matches up with my equation, and I know that's delta H positive, and the bonds formed on this side, and I know that's delta H negative. All right, up to count them now. Okay, so I've got 1 CO2, so that's 2 C to O. Okay, I've got 2 moles of NH3. Each mole has 3 NH3 bonds. Sorry, 3 NH bonds. So that's 6 times N to H. And this is where most people went wrong. They forgot about this 2 in here. Okay, so we can actually add that all up now. So that actually adds up to 3,956. So if you take the values from the table, that's 2 times 805. From the table there, and that is 6 times 391, and if you do that it adds up to 3956. Okay, so now let's look at the bonds formed. So the bonds formed are on the right hand side of the arrow. So we've got 1 water which contains 2 O to H's, so that's 2 times O to H, and in this complicated molecule here we've got 1 C to O and we've got 4 N to H's. So let's put those in. 1 times, oops, so you can see it, C to O, and 4 times N to H. And then, if we look back up here, we've got these 2 little C to N bonds here. And those are the ones we need to find. There are 2 of them. So we're going to go down here and go 2 times C to N, and we're going to call that 2X. That's the one we want to find. So if we look into the table, we've got 2 times 463. We've got 1 times 805. And we've got 4 times 391. So if we add that all up, that comes to 3295 plus 2x. Okay, so now we need to take these numbers and we need to put them into an equation. So we've got this number here, 3956, which is a positive number. And then we've got these numbers here, which have to be negative because they are releasing energy in the forming of the bonds. So I'm going to make all of that a negative. So minus 3295 minus 2x. Okay, so some of you forgot to make that a minus as well because it's minus all of that. And that's going to equal the answer. So some of you forgot to use this. So that's going to equal 89. So the last bit now is rearranging and solving this. So I just have to turn the page here. Okay, so that is 3956 minus 3295 minus 2x equals 89. Right, so what I'd do first is I'd put those two together. So let's do that. 3956 minus 3295. That's 661 minus 2x equals 89. I'm now going to get that x on its own. So you can do this in a number of ways. I'm just going to subtract that 661 across. I know some people don't like this way, but I do. 89 minus 661. So 89 minus 661 equals, it's minus 572. So minus 2x equals minus 572. So positive x, which is what I want, is going to be positive 572 divided by 2, which equals 286 kilojoules per mole. Boom. All right, that's it, guys. I'm out for this one. I know this has been 26 minutes and I'm trying to go as quickly as I can. Questions to your teachers. Have a great holiday. See you soon.